recall what we just showed, that if F is a measurable map from 0 to plus infinity, then and F is non-negative, okay, then you can see that the section of the map X determined by fixed element X of the space X. So, assuming that you have underlying spaces X and Y and sigma rather than the same notation. The integral of this with respect to the mu, the integrated integral of this. So if you again integrated with respect to the mu, you're going to get the integral of F with respect to the product measure. With respect to the product measure. In other words, if you want to compute the integral with respect to the product measure, you can compute this iterated integral of the sections. And this is what we call the Theorem's theorems. What's Fubini's theorem? Fubini's theorem, not writing it precisely at the moment, I'll write it later in a moment. But I want to extend this result for a general effect, where the F is not necessarily negative. Obviously, I want it to be measurable, but I want to relax this assumption. So the Fubini theorem would be the same with relaxing this assumption. But I know that this is equal to the positive part of F minus the negative parts of S. Okay, so in other words, I can break down every general measurable function into two non-negative, and the difference of two non-negative measurable functions, F plus and F minus, so we know it. Okay. The question is, so what's the problem? Okay, so in other words, just replace F by F plus and F minus everything, and we should be able to get what we want. But I would like to point out some of glitches. Okay, if you have F that can be written as F plus and F minus F. Okay, and what are those glitches? So what is F for me? So F is general and F is general measurable map, okay, and it's integral. Okay. And it's integral. So if F is, so what is the meaning of such kind of function being integral? So the meaning of such kind of a function which can be broken down into positive parts being integrable is that these two integrals are finite. Okay, the both of these two integrals are finite. In other words, integral that is that F plus d mu, okay, and F minus F plus the mu product mu, and it's finite, but not finite everywhere, but finite almost everywhere. That's what is a Okay, so when you go back to the definitions, you see that, okay, if it's integrable, if you have this finiteness, you go everywhere. And similarly, if f minus du and the product mu is finite almost everywhere. So in other words, the points where these two integrals are not finite has a measure 0. Okay? So this points out something interesting. So if I have this, then I can say by Bernoulli's theorem, so if this is true, then by Bernoulli's theorem, so it's not a proof, it's just a discussion actually, okay? By Bernoulli's theorem. In other words, the Bernoulli's theorem is true for f plus and f minus actually. So if this side is finite, this must be finite actually. If this is finite almost everywhere, then this side is also finite almost everywhere. So Bernoulli's theorem, this section of this f plus d mu in other words, this guy is immeasurable, obviously, and this is finite almost everywhere. Okay? Is it making sense? Now here is the trouble. So fx f plus, okay, for example, this d mu is obviously finite almost everywhere, and similarly I can say that fx f minus d mu is also finite almost everywhere. What does this mean? That there can be some points where this guy becomes infinite. So imagine I have a point x, okay, for which this guy and this guy can take any value. They can take any value. Okay? If it is immeasurable, no. This is not true. If it is immeasurable, then this could be anything between 0 to plus infinity. Okay? But it is going to be, okay, still that conclusion would have been true. It is going to be finite for the most of the times. And the points where it is not finite is going to have measure 0. So this is fine. Okay? This is fine. Now I can say that if I pick a point for which this fx f plus d mu, is infinite, but this sx f d nu, say for example, is finite. Okay. So since these are finite almost everywhere, so this means that there can be point, negligible set, where this is infinite and this is not infinite. Okay. Now the trouble would be that how would you like to define the section of f with respect to d? The natural way would be that, okay, just take simply the difference of, so just equate it to the difference of these two as the f plus and f minus, equal to f plus and f minus, so naturally you can say that, okay, just take the integral of these two. But the trouble then then would be that this guy doesn't make sense because one of them is infinite. Are you getting the point? So I'm sitting on a point for which this section is infinite while this is finite. So the difference doesn't make sense actually. So there can be some other points for which this is infinite while this is finite. So the difference would not make sense. So difference will only make sense, okay, if both are finite actually. Okay, both are finite both are finite actually.
Infinite is what we say.
I'm sorry?
Both are infinite, so is the difference.
Yes. So what we want to do? So I want this guy to make sense actually. Because if this guy will make sense, and I want to talk about the conditions under which this difference would make sense. So I would like to, give a technique to you. Because how can I avoid this problem? Okay, so how can I, deal with this situation? For this, what can I do is that let's define a map G plus. And I'm saying that G plus of X is, this section, or maybe okay. So define G plus of X as define G plus of X as F plus D nu. Okay. If this F plus D nu is finite, and at the point where this can explode, just assign it to 0. Otherwise, okay? And similarly define. So, if G plus is going to be measurable? So it shouldn't be a trouble. And similarly define G minus actually. Okay? And I want to define G of X to be G plus of X minus G minus of X. Okay? Now my claim is this expression would always make sense. Think about it. Imagine X is a kind of a point for which this is, if the both are finite, we are happy. So you're gonna get G of X as the difference of two integrals actually. So if one of them is finite, in other words, like this guy is finite, F plus is finite, okay, the integral of F plus is finite, but not other, then this would be equal to what? Integral of F plus d nu, and this would be 0. So the expression makes sense actually. Okay? If both are infinite, g of x would be 0. Okay, so this makes sense in all kind of what do you call situations. Now what I want to do, now I want to put a precise statement, a very precise statement for the Fubini's theorem. Because you can't just do a blind generalization of the Fubini theorem. Okay? You have to be careful that things should make sense. Okay. So what's a precise statement of Fubini's theorem? Okay. This statement makes form of a claim. Imagine I have two measurable spaces y comma y are sigma finite, okay, and f from calligraphic a plus b into 0 to plus infinity is measurable, and integrable, okay. Then all this is true. Then the integral of this g d mu is equal to the integral of f, okay, d, okay, tensor product mu tensor product d1, okay. Now how does this integral of g would look like? So the g is the difference, so it's roughly, okay, so if x, so if both are finite, the g would look like what? The integral of f plus minus integral of f minus. So the integral of g nu would be the way we want actually. Okay. So if one is finite, another is not, okay, then the g of x would be equal to, for example, one of these, another would be 0. So this expression looks different, but it's as per our intuition and expectation. Okay. How we're going to prove it? Prove is pretty simple. We have all done already the hard work. Okay. So as f is integrable, f which is f plus minus f minus, where f plus and f minus are also maps from, okay, the product sigma-algebra into 0 to infinity, is integrable, so in other words, this guy makes sense for f, so are f plus and f minus actually. Okay? So that's not a big deal. By Bernoulli's theorem, I can apply Bernoulli theorem to these two. Okay? Not on f, because f is different. Right? By Bernoulli's, okay, Bernoulli's theorem, okay, by Bernoulli's theorem, double integral of a section of x f plus r minus, okay, d mu is equal to, so the integral of f plus r minus d product sigma. Okay, so this is what the Bernoulli theorem both is telling us. Okay. So what is the consequence of this result? The consequence of this is, if this is integrable, finite, then the section is also integrable. Okay. So in other words, so I can say, and maybe if I write it precisely, so this integral fx f plus d nu. So in other words, if this integral is finite, in other words, the integral of the integrand with respect to d nu is finite. So that means whatever inside the integral is measurable with respect to the sigma-algebra, which is associated with this mu actually, which is calligraphic A actually. Okay? Okay? So if something is integrable, must be measurable. So this is measurable but with respect to what? A measurable. Okay, f plus minus A measurable. Okay, measurable or integrable? What should I say? Measurable. Now, almost everywhere. Now, it's not only going to be measurable but also integrable. Almost everywhere. By the way, wouldn't that be better if I call this as integrable, right?
Also,
So you have it implicitly sitting this way. So since this is almost everywhere, so I would say that let's define g plus minus of x as previously, as was integral of section of f plus minus g nu. So I'm writing the both statement together. Okay, define it if this section of f plus minus f d nu, okay, is finite and zero otherwise. Zero otherwise. If I say that E is the collection of those points for which the section Sx plus minus, okay, let's call it plus minus. So E is also plus minus, plus with respect to what and minus. Okay, collection of all for which this Sx d nu is finite, then I can write this g plus minus of x as that the indicator function of e plus minus x. I can write this as the integral fx f plus minus d nu multiplied by the indicator function of e plus minus of x, right? Let's think about it. So if x is in e plus, then it will be equal to plus actually. So if x is outside e plus, it will be 0. Okay? And both have a measurable. Now apply the definition. By definition, what would be the integral of f with respect to this product sigma algebra? Now since f can be broken down into f plus and f minus and it's integrable, so this must be equal to f plus d mu product with nu minus f minus d okay, so I can write it like that actually. Alright, and by Bernoulli's theorem, so it's like using the expressions that we have here. Okay, so by Bernoulli theorem, this would be same as the integral of section of f plus d nu minus integral of section of fx f
minus
d nu actually. Okay, so this would be
इन दोनों में से भी एक न्यू होगा, एक न्यू होगा.
yes. you will have it, and since so how can I express these in the terms of the G plus and G minus actually? Can I express these two entanglements in the terms of G plus and G minus? In other words, can I say that this is same as G plus the product sigma algebra d mu product nu, and it should be same as, so if this is finite, I'm going to keep it. If it is not finite, I'm going to keep 0 minus G minus, okay, G minus the product of tensor product nu and mu, okay. And the next, since these both are integrable, okay, so in other words, since these both are okay, so therefore I can combine them actually into a single entanglement. You can't combine them unless the both make sense. Okay, so if one of them is exploding, you can't say that. So this would be the integral of G plus of x. That would be G plus minus G minus of the product sigma algebra, and this is what that you wanted. G of d mu product sigma algebra mu active. Okay. And this is what is the Fubini's theorem. If you will see this statement in Bass' book, he has stated this generalized Fubini theorem in an interesting way, and it's a worthwhile keeping in the head. I think it's a bit bored. Okay, this is precise, but the statement that Bass has written is more explicit actually. Okay, so whenever you want to keep the statement of what do you call the Fubini's theorem, in your mind, keep the Bass version. Okay. So this completes the proof of Fubini's theorem. Okay. The final thing, and then maybe we can end the lecture, is that I can find an alternate, in other words, another sufficient condition through which this will be true actually. So at the moment, what are the sufficient conditions? That this f plus, these integrals of sections should make sense actually. In other words, this g plus and g minus should make sense. In other words, this g function should make sense. Then you're gonna have this. Now I can quickly, just a simple remark, very simple remark. I can interestingly find another situation. In other words, if f is product measurable plus infinity, integrable, for which this is true, and it's kind of a combining, and it's even better condition than. So it's that if you take the section of the function, okay, and take its absolute and integrate it with respect to d mu, and then d mu, okay, and it turns out that it's finite, then conclusion of Fubini theorem is also true. Still true. Okay?